Okay, in section 5.3 we'll continue with probability, and we're going to look at what's known as conditional probability. And when we talk about conditional probability, think back to earlier this year we talked about conditional distributions. Conditional distributions, again, were when we took a two-way table and we would only deal with one row or with one column. And we're going to kind of get into that situation as well. So what I talked about here is probably that one event happens given another one is already known to have happened. Okay, so you could look at as when you deal with a deck of cards, what's the probability I get a red card, knowing, or the term they're going to use all the time is given, I have a red card already. Okay, so what really happens is now rather than being out of 52 cards, and we're out of 51 cards. So a lot of times it shrinks my sample space down, okay, to bring it into terms of probability. So the same idea. If I have a class where there's 20 males and 15 females, and I'd say, what's the probability something happens given they're males? Okay, now I already know that the person's male, so those 15 females no longer are going to be taken into account. Now, here's our notation we have to recognize right here. Okay, notice how it's read. Probability that P, or the probability that B happens, this line right here is given. Given that event A has already happened. Okay. So, an example. Here's a two-way table from our book. We want to know the probability of L. We want to know the probability that the grade is lower than B. Well, one thing we always talk about with two-way tables again is before we get started, always fill in your marginal distributions. So when we're looking at the probability that their grade is lower than a B, we're looking out of everybody. So I am going to take the 10,000 people here. Okay? And of those 10,000 people, how many had a grade below a B? And I think I actually just have this entered in correctly. When I typed it in, I apologize. Looks like it should be 356. Okay? Now, the second one. Find your probability of E, that the grade comes from an EPS course, given the grade was less than a B. What that does to us now is now what I'm looking at is I'm only looking at the people who scored below a B. So out of those 3656, how many of them come from an engineering physical science class? And that's your 800. It's not the whole 10,000, it's just those 3656 that fall into that group that scored below a B. Now, if we go the other direction, find the probability scored less than a B, given they're in an EPS course. Okay, well, now it's given that they were in the EPS course, so they took engineering or physical science. So there's 1,600 of them. And out of those 1,600, how many then scored lower than a B? Same numerator, different denominator, it's because of our condition. All right, now we actually get into our idea of independent. Okay, two events are independent if one has no effect on the other. Okay. So, obviously, flipping a coin, comes up heads, has no effect on what happens. The next one, roll a die. Not independent. Drawing cards. Probability I draw a red card. Well, if I take that card out, now there's only 51 left to draw from. But I could make this situation into an independent situation if I have replacement. So if once I draw that card, I put it back in, now I have the same likelihood of drawing a red card again. So here's another definition. We're going to deal with it in a couple different ways. We've already kind of talked about how to show things are independent, but this is another way. Okay. if the probability that A occurs given B has already occurred is the same as the probability of A, then those two events are independent. Because what it's saying is that B's already happened. And so if that probability of A is still the same as what the probability of A is by itself, obviously B had no impact on it. And then all they do in the second one is reverse it. Okay. Are these two events independent? Okay. So what's probably male? Okay, we're going to call it M. And left-handed, are they independent? So one of the things I can do is I can look at those definitions and just go in and change A to maybe L's and B's to M's. And so what I want to do is check those. So the probability if somebody's a left-hander is 7 out of 50. Probability they're left-handed given they're a male. So now, given they're male, I'm only dealing with those 23 people. And of those 23, 3 of them are right or left-handed. So right there, we know that those two aren't equivalent, not independent. We looked at the other situation, which we don't have to do because we already showed that that didn't work. Probability someone's male was a 23 out of 50. This time, given they're left-handed, so that's your 7. 3 of them are males. Again, not equal. Then you can type them in to see your decimal values. Okay. Or we could go to the other definition, which I talked about a lot of times. It's easier for people to look at. It's probability that both occur, so the probability that they are left-handed and male. Okay. Which are these 3 out of 50. Is that going to be equal to the probability they're left-handed, which is 7 out of 50, times the probability that they are male, which is 23 out of 50. Which again would not be equal, so not independent. All right. Now, we can also draw some of these things up using tree diagrams again. We dealt with some tree diagrams earlier in terms of looking at what my sample space could be. So consider flipping a coin twice. Okay? So when I flip the coin twice, on my first toss it could come up heads or it could come up tails. My second toss, then if it was heads on the first, it could come up heads or tails on the second. Same thing if it was tails on the first one. And what I can do now is look at what's the probability of 2 heads coming up. I can go in and along each one of these branches, list my probability. Probability that it comes up heads is 1/2. Probability it comes up heads is 1/2. Probability it comes up heads is 1/2. Okay? Probability it comes up tails is 1/2. Okay? And what happens with this tree diagram, if I want to know certain probabilities, probability 2 heads, what I want to do is follow that path. And we're saying that these two things are independent. And so therefore, because they're independent, I can multiply the probabilities. Now, another thing that happens, if I filled in the rest of this, probability it's heads and then tails, again, it'd be 1/2 times 1/2, which would be a 1/4. Probability that it's tails, then heads, you're going to get the same thing. Probability 2 tails, also 1/4. One of the things that we can always go through and check then, is those are all my possible outcomes. So all those probabilities at the end of my tree diagram have to add to 1. So for example, picking 2 lefties. Okay, what's the probability if this is my sample space here that I pick 2 left-handers? Again, what I always would do, okay, is fill in my marginal distributions first. So, first person that we choose, okay, they could be a lefty or they could be a righty. Now, probability they're a lefty, 4 out of 28, or 1 out of 7. Probability they're a righty, 24 out of 28, or 6 out of 7. Choose our second person. Don't care about that first one. Okay. left, but they're going to be a right, they're going to be left, they're going to be a right. Now, this time they're not independent anymore. Okay? This time we're down to 27 people. Okay? And of those 27 people, how many are left-handed? Well, I took a left-hander out already. Okay? Meaning that there are only 3 left-handers left. Probability of a right-hander, 27. I didn't take any of those out, so that's your 24. Okay, which if we simplify it down becomes 8/9. Should simplify this down to 1/9. Okay. If I go down to the bottom, probability of left-hander. This time I haven't taken any of my left-handers out, so it's going to be 4 of those 27. I did take a right-hander out, so I'm down to 23 of the 27 left. For the right-hander. So if I want to find that probability of getting 2 left-handers, what I'm going to do is follow that trail. And I'm going to look at the probabilities along the way. 1/7 times 1/9. My probability is 1/63. So that can be helpful. Now, your general multiplication rule. Okay, this again, like our general addition rule, works in any situation. Probability that both events A and B occur is going to be equal to the probability that one of them occurs times the probability the other one occurs given the first one occurred. Okay. So this could also be written, it's probability of B times probability of A given B has already occurred. Now, what I always tell people to keep track of, you have both your events listed, and then the second case, what we're doing is we're bringing with the fact that the first one already happened. All right, so then multiplication rule, we've already talked about this independent events, and that's probability of A times probability of B. This is what I use to check for independence. You can also use that earlier conditional probability rule to check for independence, but you can use this one, and a lot of times this one's a little easier. All right, just a quick tip. You can write your statements like probability of A given B if A and B are clearly defined, or you can use a verbal equivalent. Okay, and I prefer to write the words in. I think it's easier than trying to follow, okay, what was event A and what was event B. So as I put here, the probability that somebody read the New York Times given they also read the USA Today. Otherwise, what you need to do is talk about A as the event that somebody read the New York Times, event B, probability that, or I mean, the event that they read USA Today. You have to do this. All right, then just one last little thing that comes up is what we talked about is false positive or false negative. False positive, okay, means you get a positive result even though you shouldn't. So for instance, a lot of times they use it with athletes and drug testing, and things like the Olympics. A false positive would say that you tested positive, okay? But you're not really using drugs. False negative, you would get a negative test result, even though you shouldn't. Okay? So you're using the drugs and you get a false negative. Okay? So that takes care of our conditional probability piece and probability.